So welcome everyone to the HAO Columbia. Today we'll have a tech team talk. We have Charles Mecklenburg, a professor at Montana State University, studying the energization of the solar atmosphere through space-based observation in the ultraviolet, extreme ultraviolet, and soft X-ray wavelengths. Charles is the PI for the FURST instrument, which we'll hear more about in a couple of minutes. And he has led 4 other suborbital rocket flights. And he's also PI on the IRIS mission and the MUSE mission. Then we have Kathy Bunn. She's a PhD candidate in the solar physics group at Montana State, and she's also a finalist fellow. Her research interests include sun stellar collections, transition region and explosive events. Her contribution to the FURST mission includes optical alignment, focusing, testing, calibration, integration, and testing as some launch operations. In addition, she has a master's degree in physics, and she has a formal training in art, which you can see by the nice logos that she designs for the different missions. She worked in the past with ground-based near our LiDAR for atmospheric profiling, and she has shifted to the far ultraviolet, then looking at the sun. Our next tag team speaker is Suman Panda. She's also a PhD candidate in the Department of Electrical Engineering at Montana State, and she has a master's degree in physics. Her work focuses on solar physics and instrumentation, and for this project, she has done alignment, integration, testing, and calibration for the rocket instrument. She's originally from India, and she's passionate about hands-on experimental research and outreach, and her long-term goals are to contribute or design innovative space instrumentation missions. Without further ado, I'll let them take over, and thank you again for coming.
Thanks, Dana, for inviting us to HAO. Thank you all for coming today. We'll be taking a look at FIRST, the Full Sun Ultraviolet Rocket Spectrometer, an only slightly tortured acronym. And it's a NASA heliophysics suborbital rocket. I'm not usually a fan of reading through abstract slides, but it suddenly occurred to me I didn't have an outline. So the idea of FIRST is to place the sun in context with a great many stars observed by Hubble, providing the first high-resolution solar reference spectrum covering 120 to 183 nanometers. So that includes Lyman alpha, all the lines that are in IRIS, so on, but in a really broad swath of spectrum. So we'll give some highlights of the scientific motivation. We'll go into the instrument design and construction and the lessons learned. And since we have launched this once, but you'll see there's a caveat to that. And we'll also put up some objectives and plans for reflight. Now, I'll say that we're going to try to walk through this in a way that gives you a little bit of a feel for what it's like to put together a mission like this, and what we've the interesting challenges, let's say, that we've encountered along the way. I need to mention that it's not just us. This is a collaboration between Montana State University, HAO, and Marshall Space Flight Center. I'm the PI. You've met my 2 grad students here. Many of you have shaken hands, and they were just introduced. Also, Roy Smart, who's pictured somewhere here. There we go. There's Roy. So he's in on the chat back home. Jake Davis, I saw, is actually dialed in. Ruben Michael is another engineer on the project, and Tyler Holliday is our PM, with a lot of backup from Larry Springer, who's our really experienced guy who keeps us from running off the rails. And at HAO, Dana is our co-I. I'll tell you a little bit about how Phil Judge actually inspired the whole thing. And at Marshall Space Flight Center, Adam Kabelski is our co-I. Originally, it was Amy Weinbarger, but she handed it off to Adam, but she's still involved. And Jen Vigil is our master of calibration things. Lots of acknowledgements. I won't go through them all, but I'm grateful to HAO for giving me an office for a month. It was an office that came with funding. There's a jar of like 500 pennies on the shelf. I don't know where it came from. I haven't decided how to spend it. Maybe I'll use it for lunch today. This all started back in May of 2017. This is a letter that I got from Phil Judge, and he quoted something from a paper that he was writing where he said, "It is a pity that no high-quality sun as a star spectrum in the commonly observed vacuum UV region has been obtained." And I was like, Phil, this has to have been done in 1983. You just missed a paper somewhere. But we did a lot of digging through the literature, and sure enough, nobody had done this. Nobody had a sun as a star spectrum at high resolution in the far ultraviolet. So we set about thinking about what should be the next steps. You might ask why we want to do this. Why would we care what the disk integrated spectrum of the sun is? Well, first of all, it would place us in context with the many stars that have been observed by Hubble. There are lots of things that we can look at there. There's, for example, supersonic broadening in all of the optically thin transition region lines. So transition region, for those who aren't solar people, that's the roots of the corona, where the corona interfaces with the underlying chromosphere. It's a very key region for the energization of the solar atmosphere. And then there's various metrics of magnetic activity, including transition region line intensities and UV continuum, and hopefully the optically thick line profiles, although it's hard to understand them sometimes, gives us some clue about the atmospheric structure. I was just noticing the other day, there's a Judge 2017 paper that shows these nice, deeply reversed carbon-2 1335 lines for alpha Cen A. But when you look at the disk integrated sun, what we see from Iris, since Iris is of course very narrow band compared to FURST, but does have this line, you don't see an average reversal. There are regions that have a reversal, but in the aggregate, it's not reversed. So that's got to tell us something about the structure of that atmosphere. Also, solar system objects, including Earth's atmosphere, which is also in the solar system. These are all excited by FUV radiation from the sun. And so having accurate line profiles could actually matter, especially when you have a fast-moving object like, say, a cometary atmosphere that sees a Doppler-shifted version of, say, Lyman alpha, right? So that's going to change how the absorption works. The kicker, though, is that we can't just assemble this from the data that we already have. We have some narrow slices of that spectrum from Iris doing full disk mosaics. We have other missions that have done things at low resolution for the full disk, but you can't see line profiles or even necessarily distinguish lines in many cases. And so really, we just don't have what we need to assemble this. So how do you do it? This was our first sort of silly idea. If you could fly like a marble or a ball bearing out in front of Hubble, the virtual image of the sun would look like a star, and you could just use COS or STS, the onboard spectrometers in Hubble, to take the FUV spectrum. That'd solve it right there. But we couldn't figure out the formation flying problem for the marble. So I will let Suman describe what we really did.
Since we decided that flying a ball bearing was out of question, we came up with a spectrometer design that can be flown in a sounding rocket. And so up here we have the optical layout of FURST. It's a Rowland circle spectrograph. What's unique about this design is it's got a spherical grating where the radius of the grating is equal to the diameter of the Rowland circle. And this concept was first proposed by Henry Augustus Rowland, and hence is named after him. So what that lets you do is, for any sources on the Rowland circle, the dispersed component are focused back on the circle. So it helps with focusing, and so we don't need to have additional focusing elements in our system. So I'll walk you through a little bit of how our instrument works. So we have sunlight coming in, and they get reflected by these feed optic. And what they are they're cylindrical elements of glass that are coated with reflective coatings. They form a virtual image of the sun. In a traditional spectrograph, this is where you would have your slit. So we focus the sun onto something like a slit. This then get dispersed by the grating, and the dispersed components are imaged by the detector. We are ambitious and we want to measure a broad swath of the FUV spectrum. So we aim to get from 120 to 183 nanometers. To do that, with just one feed optic, you would need a much bigger detector than is commercially available. So to get around that, we try and make use of different incidence angle by having 7 different feed optic channels at 7 different incidence position. And instead of, say, like moving this feed optic, which you can also do, but having 7 different channels gives us repeatable incidence positions. And these feed optic are operated one at a time through a feed optic array, as you can see in this zoomed in image. And this is a solid model of FURST, which is much closer to how FURST looks in reality. So these feed optics are controlled by a rotary solenoid that moves the casing, and that controls the open and close position of the feed optics. So these little slits, they move to open and close it. So in flight, we have 8 channels, 7 corresponding to the 7 open channels of the feed optic and 1 for the dark, and we run through them sequentially. We just had one tiny problem at the start of our instrumentation journey, where we weren't able to find any vendor that would be able to make these feed optic for us. As you can see, you see a little sketch of what we were requiring of them. We want a glass rod that's 6 millimeters diameter and about 38 millimeters length. But it turned out that nobody was ready to make that for us. So in true rocketeering fashion, we put on our thinking caps, and we basically had to get nifty to try and make these. So what we did was we used these stock glass rods that I have a picture of here. They're borosilicate rods, and they're usually used, you see it in your chem labs for like stirring chemicals. So just your regular run-of-the-mill glass rods. They were never intended for optics application. You never know if it would work or not, but we suspected that the way they were manufactured, the tolerances on it would be good enough. And so I took a mechanical Dremel to these long glass rods, cut them up to our desired dimension, cleaned them, and manually visually inspected them under a magnifying glass. So it turns out that the most problem we encountered with these glass rods were due to how they were packaged. Since they were not intended for optics application, they were packaged in cardboard material, and that led to a lot of scratch on the glass rods. So we had to visually inspect and get rid of the sections and kind of pick and choose the good sections. But just doing it visually wasn't good enough. So we wanted to actually quantify it. So we came up with this simple experimental setup to measure the focus image of these feed optic. So in this setup, we have a green laser light that basically goes through a beam expander of sorts with the spatial filter and the lens. And then we have the beam redirected onto the feed optic. So then that forms a virtual image at the focus, and that focus is imaged by the camera through a 3x magnification, so we can look at it closely. With this experiment, our motivation was to minimize the effect of aberration that's introduced to our system from the surface imperfections of the glass rods. So I came up with a requirement of full width half max on these focus images of about 5.5 pixels. And here on the left, you see a focus image that's seen by the camera. And it's nice and sharp, and it looks pretty narrow. But to quantify it, I sum all of these pixels vertically. So that's shown on the image here in the middle. You can think of it like almost like a line profile, if you will. Now, if these rods were placed kind of tilted with respect to the detector, that tilt, when you add it up vertically, will lead to a artificial broadening in your line profile. So that wouldn't give you a true full width half max. So to get around that, we analyzed just smaller chunks of these. And sum the smaller chunks vertically. And I have all of those plotted in the image here on the right. So then we look at the statistical distribution of these full width half max. We look at the median, and we look at the maximum full width half max that's present in all of the one specific glass rod. And we make sure that all of them satisfy our criteria of being below the 5.5 pixels. For this particular case, the median full width half max was around 2.55 pixels, and even the max was well below the 5.5 pixels of requirement. So it turns out at the end, we did find usable glass rods for our purpose. So we sorted out 14 of them. That's 2 sets for our instrument, and we send them off to Acton Optics to be coated. And now Cappy will talk about how we actually built the instrument.
Thanks. All right, so at this point we have all the optics and we're confident in their quality. So next was optical alignment. So using a fiber coupled Heaney laser, we aligned the grating such that it placed the round circle where we needed it on the optical bench. Next, we ensured that the 7 cylindrical feed optics were aligned with each other and the optical bench using a Heaney laser sheet. And that's shown here. You can see the reflection. So here are the feed optics. They're reflecting a laser sheet onto this, what I call a movie screen. And this allows us to easily check the tip and tilt of each feed optic. And then we also use a theodolite to ensure that the coated sections of the feed optics would be centered in the beam path. And that's all the optics. So the next step is focus. FURST is designed to measure the far ultraviolet, which does not propagate in air. So to focus first while in air, the grating was designed with additional sections ruled for visible light that kind of sandwich the FUV section. So I have an illustration here of the 2 visible ruled sections. And then these are also masked off during flight. So our focus procedure also has 2 steps. First, the array of feed optics is translated on a stage to collect a focus curve for feed optic channel 1. And then that one's placed in focus. And I have an illustration here. So here's the round circle in red. Here's our array of feed optics. And we're moving this lower stage until this first feed optic is in focus on the round circle. Second, the array is then pivoted about feed optic 1, and a focus curve is collected for feed optic channel 7, and then that one's placed in focus. So here's our second step, rotation. So it's the second stage is designed to pivot exactly under the first feed optic, and then we get this last feed optic in focus here, and yeah, let's see. And since the feed optic array already matches the curvature of the round circle, the remaining feed optics will also be in focus, and I was able to check that too. And given that for these 2 steps, I only needed to focus the first and last channels, I found that a krypton calibration lamp worked well for channel 1, which images the blue and violet wavelengths, and a neon lamp worked well for channel 7, which images the red wavelengths. All right, so with the instrument focused, I could now insert the visible blind filter that goes right in front of the camera. And this is meant to reduce stray visible light on the detector. However, upon closer inspection, we found that it had arrived with pinholes in the coating. And so with what time we had left, the best we could do was patch them. So I cut tiny patches out of this adhesive-backed aluminum, and then I carefully placed them over the holes. And so I think I now know what rocket surgery is. That worked. All right, so once everything was assembled, oh, sorry, here's first, once everything is assembled. Please note that we do, in fact, have baffles. This will be important later. Here's our avionics section. Here's our array of feed optics. You can see the gears up here that are connected to the rotary solenoids. Behind that is the shutter controller that controls these solenoids. Up here we have this copper piece is the cold block, and that's connected to the camera, which is here. Here's the filter housing in front of the camera. This tubing here is the LN2 plumbing that cools the cold block. Following it back, we have the grating kind of peeking out right here. And then lastly, you'll see we have a reference mirror at the very back there. And we use this to align FURST to a calibration system that was designed by Marshall Space Flight Center. So here's that calibration system from Marshall Space Flight Center. And it's shown connected to FURST back here. So this system, it radiometrically calibrates FURST using a deuterium lamp as the FUV source, and a NIST traceable photodiode. And on the right is an example of our first attempt at calibration. This wasn't a successful attempt. We're still working out some kinks with the calibration system. But this image does demonstrate that we successfully focused FURST in the FUV, which was very exciting. The other interesting thing you'll notice, quite obvious, is this oval in the center. And this is made up of strikes from an from a 1 millicurie iron 55 X-ray source that we use for in-flight gain calibration. So I had designed a collimator that would direct the X-ray beam to the center of the detector, so that it covers one corner from each of the 4 taps that make up the detector, so that we can measure the gain from each tap. And this image was exposed for much, much longer than a flight image. So typically we wouldn't have like this dense of an oval with like overlapping hits and stuff like that. And then here I have just a picture of the iron 55 source that we are using. Yeah. Okay. So now that the instrument's ready, we plan to calibrate after launch at this point. So next we shipped it along with all of our ground support equipment and basically our entire lab to White Sands Missile Range, New Mexico. Here, the NASA sounding rockets launch from Launch Complex 36, which I've marked on this map down here. And we can't take photos of the outside of that building, but I found this photo from around 1963 that shows LC-36 and the launch of Little Joe 2. Building basically looks exactly the same at this point. So on the map, I've also marked the approximate location where NASA sounding rockets land, which is about 50 miles downrange. So for these sounding rocket launches, we stay in New Mexico for nearly a month to accomplish all of the integration and testing that's required to pull this off. Here's an extremely abbreviated list of what leads up to launch. We do post-shipping functional and alignment checks, handshaking with telemetry and buildup of the payload. Next is Vibe, where the instrument is shaken until all the scientists have heart attacks. And then this is preceded and followed by sequence tests. We do post-Vibe alignment checks on the optics, make sure nothing moved. Then gravimetrics, which is where they measure the mass and center mass, and they spin it around and get measurements that way. Then we move it to the launch rails and attach a couple motors, do more sequence tests and a horizontal and vertical dress rehearsal. Then we say go. Next, I'll show a video, the first 30 seconds of launch. And in the corner of the video, I've embedded a synced view from the camera on board the rocket.
Thing's really good.
Yeah. Okay, so that's the first stage. It's done. And then the second stage will light. Yeah. And we had an awesome cameraman, and he caught the first stage on its way back down. Suman and the rest of the crew, they went out there and dug up the fins from this thing as souvenirs, while Charles and I flew in a Black Hawk helicopter to go get the actual instrument. That was pretty fun. Okay, next, Suman will go over the data we got.
But everything during launch, all of the components of the rocket appeared to work nominally. But then we got this data. Well, as you know, like data is supposed to have ones and zeros, but we only got ones. And all of our frames after the door was open was saturated. And as you can imagine, this was pretty disappointing for us. But there were a couple of reasons that immediately came to our mind as to what could have gone wrong for us to get the saturated data. So we did some sanity checks as soon as we, and by we, I mean Cappy and Charles flew down and recovered our payload. So we checked that the alignment of LIST to our payload was maintained during flight. So LIST is the instrument that points us to the sun. So if that alignment was compromised, then basically there would be scope for other brighter objects to be in our field of view. But it turned out that that alignment was maintained during flight. Then we checked for if our visible blind filter that's right in front of our detector was intact, because failure of that would again cause a lot of visible light to flow into our detector. And we found that the filter looked mechanically intact. We also considered that there might be some glint off of our shutter door that could have allowed light to get into our system. But then we looked at a few solid models and did a little experimentation to basically convince ourselves that that was not the possibility. So at this point, we didn't really understand the reason for the saturated data, even though we had a lot of ideas as to what could have gone wrong or why we had saturated data. So we thought to take advantage of a heliostat facility that they had at Wismar to hopefully recreate the problem. And we hope that that would help us narrow down the source of the problem. So a few of our teammates, they stayed back at Wismar, and in this picture here, you can see we have our payload aligned to the heliostat, and we were in fact able to recreate the saturated frames that we saw during flight using the heliostat. So that gave us an idea that the problem was one of the main sources of problem was visible light from the sun. To get a better idea, to pinpoint like where we were seeing the stray light from, we used a tiny little visible camera with a fisheye lens that's got a big field of view, and we plopped it right in front of our flight camera. So this allowed us to see the system from the field of view of the camera. So we had, in the top direction, we still had the alignment to the heliostat, and our fisheye camera was looking through the baffles. It had basically the whole view of the instrument from the camera's perspective. And this was really informative because we learned really useful stuff with it. So this image here is what the fisheye camera saw. And the baffle that you're seeing is the rearmost baffle. It's the baffle that's directly in front of the camera. And as you can see, it's really, really bright in here. And we narrowed down, or we pinpointed a couple of different sources that are mentioned with this red arrows. The first source was a direct path from our detector to the outside, a couple of degrees off the sun. And we were aware that this direct path existed, but we were not too concerned about it, because even though we know that the K corona exists a couple of degrees off of the sun, the field of view of this direct path was not large, so we thought it wouldn't really matter much. It looks much more brighter in this particular picture, because here you can see, the bright New Mexico desert that's out there, which would not happen in space. So, so we're still not too concerned about this direct path. The second source you'll see is the baffle itself. And this was really eye-opening because we thought we had, blackened the baffles as best we could. We had bead blasted them and it was black anodized. But as you can see, it still looks a lot shiny. And that contributes to a lot of the stray light. Then the third source here is a reflection from the clear section of our grating that's between the FUV ruling and the visible rulings. And this is not a real source, I think, because we're looking through the fisheye camera, which is not very well aligned to our flight camera. So any difference in tip and tilt of it can change the perspective of what you're seeing. So we don't think this is a real contributor to the stray light. And we did verify it by looking in there with a dental mirror and making sure that that was not visible through the baffles. And the fourth source is this really shiny edges of the baffles that they seem to reflect a lot of the stray light as well. So now that we had identified the sources of the stray light, we wanted to do some calculation to understand it better. So the largest source was from that rearmost baffle. That contributed most. It was really shiny. And we're getting sunlight directly streaming on our feed optic array. And even though it's blackened, as we saw, it's not really black enough. So any reflection off of this feed optic array and then off from the baffle, that's two reflection light could end up on your detector. So that seemed significant. And this yellow shaded area here shows the field of view of the camera. So that's the part of the baffle that the camera can see. So any stray light or any light that gets reflected from here more likely will end up in our detector. And so I did a really simplified version of the calculation where we consider some light that gets bounced off of the feed optic array onto our baffle and then back onto our detector. For this particular case, I considered both the feed optic array and the baffle to be Lambertian reflectors. And what that means is for any incident light, they reflect equally into all directions, which seemed like a good assumption to make. Considering that and considering the reflectivity of our black coating, we found that the signal that would be expected in our camera is at the order of 610 to the 4 DNs. And what we saw in our saturated pixels were 10 to the 5 DNs. So that's very comparable. In retrospect, one of our main disadvantages of FURST is the fact that we have a big aperture out at the front that lets in stray light, so all of the 7 channels can get illuminated. But for any one particular data point, the geometric aperture is really, really small. We really are collecting light from a very thin strip of that feed optic. So that geometric aperture is almost 2,500 times smaller than the total aperture of FURST, which means that we are letting in 2,500 times more light than we really need. So that means we are letting in a lot of light in our system. Then, to make matters worse, the ratio of visible to FUV emission for the sun is of the order of 30,000. Now, our filter, the visible blind filter, does help a little bit because the filter rejection for the visible to FUV is 10 to the negative 2. But if we take just all of these into account, that means that the ratio of visible light to FUV light in our system is almost 10 to the 6. So that's a lot of light that we don't need. I think therein lies the crux for the stray light problem for us. So now Cappy will tell a little bit about what we did to quantify the stray light problem more and what we are doing to fix it.
Thank you. Okay, so after our successful recreation of the problem at LC36 with their heliostat, we wondered how we might go about retesting it at MSU between any adjustments that we make to our baffling system. Well, the awesome folks at LC36, they let us borrow a large mirror that was in storage, and we got, and then at MSU, we got permission to use a satellite lab space that would allow us to shine sunlight right into the instrument. So these images kind of show the path of the sunlight. First, our manually controlled heliostat points sunlight at the instrument. A sophisticated alignment tool known as paperboard with a hole in the middle is used to create a narrow spot. This spot then reflects off of our reference mirror, and it should land centered on the hole in the board. If not, the heliostat is adjusted until it does. And then finally, the paperboard is removed from the beam path, and we take images with the FIRST camera using our ground support equipment shown here. So since the images are completely saturated at the flight exposure time of 10 seconds, we're using 3-second exposures instead. After subtracting off the dark, or rather gray in this case, we get this image, which has a median value of about 38,000 DN. So the first source of stray light that we wanted to address was that reflecting off of the baffle that's just in front of the camera. And this was accomplished by installing a tunnel that goes from the camera head to the face of the baffle that's in front of it. And the median value of this image is about 5,000 DN, which is about 14% of the median value before the tunnel was installed, making it a pretty successful addition. Okay, so our next idea, unfortunately, took us a step backwards. It was meant to address the stray light that's from the direct path that Suman mentioned earlier. This path shouldn't be an issue in the darkness of space, but it's definitely an issue in the brightness of snowy Montana. Our initial solution to this direct path issue was to install slats that are parallel to the beam path here. Let's see. And this would block the camera's view of the outside. And then we also included scrapers on both ends of the slats. These are the scrapers on either end. And this would prevent direct sunlight from grazing the slats. Unfortunately, even though the slats were bead blasted and black anodized, they seem to reflect indirect light at grazing angles right into our camera, as we can see from this image down here. So we got rid of those. Okay, so the next idea that we're working on is trying to better simulate the darkness of space outside the instrument. We're going about this using sonotubes, which have been painted black on the inside and they have baffles in them. This is still a work in progress as we're trying to diminish the light coming in at grazing angles. We've also just heard of earlier this week that we may be able to use the NCAR vacuum tunnel facility and its heliostat or sun simulators. So we may be back in Boulder soon with a rocket payload. Some other ideas we may try, they include sharpening the edges of baffles to remove any grazing angle glint from those, or coating the baffles with a darker material, something along the lines of like a Vanta black. Some more involved solutions would include placing a sliding shutter at the front aperture, so only the open field optic channel would receive sunlight, or installing a second visible blind filter, which would entail refocusing the instrument. Well, in any case, we're confident we can solve the stray light problem, and we're excited for the prospect of a reflight. Let Charles take over from here.
All right, I'll just wrap it up by saying we have a fully functional payload, but it has a serious stray light problem. We think we understand the causes and have got it at least roughly quantified, and we're making progress toward a solution. There's still the radiometric calibration pending. We've proposed a reflight, aiming for a fall 2025 launch. We hope to hear about that next month. I hear that NASA is still conducting review panels, so on the edge of our seats here waiting to hear about that. But as we look further forward, assuming that we get this all together and get some useful data the next time around, what then? Of course, the sun is a variable star. There is a solar cycle. There are active regions that rotate on and off the disk. There are flares, which are very short-term variability. And all of those are things that we could begin to address with future rocket reflights. So we could simply recalibrate, refly. You may have heard there was a successful flare sounding rocket program or campaign last spring that managed to catch an M flare from Poker Flat. So we might try to propose to repeat that feat with this instrument and get transition region flare spectra. That would be an interesting thing to do. And then in the longer term, we've also started looking at designs for compactified versions of FURST. We think that not only the optics, but all that we would need for power, attitude control, telemetry, and so on could be fit into a 12U CubeSat. So that'd be cool. We could get spectrum every day or several spectra a day, maybe include a little flare monitor so that we can respond to flares. So we have lots of thoughts about what to do with this in the future. With that, I'll just close and invite you to ask questions. Thanks.
Thank you. Any question? Yeah.
So we understand your pain at HAO. We deal with coronagraphs. We have to reject line. We're trying to get down to 10 to the minus 9 in our outer field of view. So a couple of things you're doing are totally the right approach. Anodized black does not reject straight light at the levels we all need in this room right now. So you really have to go to, you mentioned Vanta black. There are definitely some much better coatings out there that truly reject much more of the light because we have the same problem. And we found just recently some black honeycomb material from ACTAR that we're going to be inserting in our light dump to try to knock some of that down. I don't know if it's going to be good enough for what you're doing. The other thing we did on the front end, we learned from our previous chronographs, the out of band rejection is really important. And we did a lot better trying to knock down. We have a blocking filter on the blue that does a good job, but there was a lot of red light getting in to our earlier chronometer up at Mauna Loa. So we had special requirements for our out of band rejection on the red to get down to like, we wanted like 10 to the minus 9 or 10 rejected from that side. So that's another possibility. I don't know how that works with EUV, with the short wavelengths you're looking at. I don't know what's available.
Yeah.
But those things both help.
Yeah, one of the things we've actually initiated, there's that we didn't mention, there's a little project going on now at MSU. We have a group there that works with nanophotonics. And so they're looking at trying to design a more efficient visible blind filter for us. So they've made a little bit of progress. I think they're up to like 1980s technology now after only, a few weeks of playing, and hopefully they'll get further than that, because I mean, what we're flying is Hubble era technology, right? Just your Actin, Teledyne, FUV filters like they flew on Hubble. So yeah, thanks for the suggestions. That, as you might imagine, that's one of the reasons we came here, right? We knew that there are lots of people working on coronagraphs and things like that in Boulder. And so we've met with a number of people and, talked this over just kind of informally. We've got a good list of suggestions. Thanks for mentioning the ACTAR honeycomb stuff, because I don't think we'd heard that particular one before. We also have some other materials that we've been playing with from other vendors. So yeah.
Yeah.
Lots of options.
Have the better black hole you
Noticed that.
do.
Yeah.
Noticed that. I hope we asked NASA for enough.
Any other questions?
So you've been saying it's a high resolution spectrum. What is the resolution?
Resolving power around 30,000. So yeah, enough to resolve line profiles. We should see, I somehow the thing that intrigues me the most, even though it's not like our main science, I just really want to see the centrally reversed hydrogen Lyman alpha line with a little notch in the middle from the geocorona. People have measured that before, but I've never measured it myself. We don't see that. Yeah.
So how does that compare to the available stellar data sets?
Yeah, the stellar data sets are fantastic. The resolution of Hubble is even higher. You could argue it 12 different ways how much resolution you need, but for my money, if I can resolve the what would be the thermal width of like 100,000 degree transition region solar line, they're all actually wider than that thermal width. But if I can resolve the thermal width, I probably can resolve all the details within that profile. So we came up with a requirement of around 20,000 and we hit more like 30,000.
I don't know much about the timescales in rocketry, but I guess 2 or 3 minutes of observations.
5, yeah.
5, and at 10 seconds, so you're getting what, 30 images?
Yeah.
Okay. Is there a way, could you play games with that sequence to dither the orientation of the instrument or the pointing to sort of tease out some of these things in a post-flight analysis, as opposed to getting all 50 images identically saturated? I was wondering if there's a way you could structure your experiment to.
Yeah. Well, of course, if they're really saturated, then there's no information, right? But I'm sure what you mean is, once we've got the stray light down to a level where we can try to process the data and subtract it out, right? And those are things that we have to think about. One of the concerns we have is that when we actually have a shutter open, I don't know if we mentioned those saturated images are even in the darks, right?
Oh.
Because we're just reflecting off this black thing to that black thing onto the camera. Right. So that's all going to change when we open one of the feed optics, and we'll actually get some intentionally reflected light, but visible will come along with it, right? That's going to alter that background that we have to subtract out. So yeah, we've talked a little bit about how to pull that all out. I think we can get a lot of information from ground testing, but ultimately, maybe little modifications to our exposure sequence. I really hesitate to do a whole lot of maneuvering in space. I don't think it's going to be a very role dependent thing, because the Earth is way down here. It's it's in the summer. We're pointed toward the sun, so the angle's pretty high. Earth's limb is way down here, so hopefully that's not a problem. We know that geometrically we cannot see our shutter door, so hopefully roll angle is not a big deal. But yeah.
Any questions in the room? Any questions online?
Oh, a final question about the payload after it crash landed. Was everything just when you were doing your post-flight testing? Was everything fully intact and you didn't need to do anything to it?
I think so. I don't remember.
Is that normal for these rocket flights? That again, they kind of
Yeah, there's no damage. It still works.
Yeah, I've certainly had payloads that were damaged.
Yeah.
I could tell some fun stories about that, but
And like we have telemetry, so like I could see in real time the images coming down and it just being wiped.
Sure.
So it wasn't like data got changed or something upon.
Yeah.
Payload came down on a parachute. The
Yeah,
thing
yeah.
you saw in the video was the.
oh yeah.
Yeah, that's true. I mean,
yeah, that wasn't the payload coming down. It's just the carrier booster. Yeah.
it's not exactly
Thank you.
soft either. Like,
Yeah.
Yeah. It is a rough landing. I
And
mean,
we
we gotta
did land on our belly, but
we have a big
thankfully we
dent.
didn't
Yeah.
damage anything.
And-
So
and actually, it is a good point that there can be damage that's hidden. I've had things that flew like, several times, and then on the third flight, they finally came apart. And so that's obviously a concern. I wish I had a magical metal fatigue meter that I could use. There's some testing like that we can do, but no, it's very easy for a hidden crack to be there.
Kevin?
Do you have requirements on how low you'd like to get the scattered light? What sort of ratio between scattered light, your spectrum
Well,
is tolerable?
So, even if we were to get down a couple of orders of magnitude, which I think we're probably getting close to if we're really in space with the tunnel baffle that we have, that's probably at the point where we can start saying, let's try and just subtract the rest off in post-processing. If you want to know the fantasy answer, I'd like to take it down by a factor of 10 to the 4. And, then we would basically be at the few DN level on the sensor and, have very high signal to background. I don't know how far we'll get, but we'll get however far we can with the resources that we have and get a flight where we can at least see a spectrum, and then we'll take it from there.
Do you have the ability to create straight light models in a software analysis package like a Fred or any optical engineers that can support your team?
Short answer is sort of yes. We could run Zmax in non-sequential mode. We don't have experience with that. I tend to put a little more stock in back of the envelope calculations, honestly. Things like what Suman was showing. Those are simple enough models that you can understand what the assumptions are and not fool yourself. And I'm not saying that, you're always fooled when you have a high fidelity model, but I have seen many cases where we have high fidelity models of, let's say a structure, right? You do an FEM, and you think you understand what the modes of your structure are. And then you go and vibe it and you find out, well, those aren't the modes that we predicted, right? I don't think I've actually seen that loop closed very successfully. At least not at a university level, and maybe even not at the level of some of the big aerospace companies. It can be very hard to get a high fidelity model exactly right, because little niggling details about boundary conditions and things can make enormous differences. So I don't know. I'm certainly open to trying it, but I wouldn't believe it until the back of the envelope comes close to the same answer.
The colloquium yesterday, the speaker put up a quote, "All models are wrong," or somebody put it in the chat.
Yeah.
But somebody,
If we're honest, yeah, and it doesn't mean we shouldn't model, right? I mean, obviously you should try and model things, but I think what I'm more focused on right now is we have the ability between the instrument camera and this neat little fisheye thing that we can use to explore light leaks. We can do guess and check and keep reducing the level step by step. So I think we've got a decent methodology, and I trust those measurements more than I trust anything I can calculate or model.
Any other questions, either here or online? If not, let's thank the speakers again. And they're here until the end of the week, so
exciting.
please ask them questions.
Thank you.
Yeah.
What happens when your grad students graduate?